Welcome to the Vivado Quick Take on power optimization. In this video, we'll review some of the key factors that affect power consumption in an FPGA, how Vivado helps to minimize power consumption in your design, and finally, we'll take a look at some of the advanced control and best practices for getting the most out of Vivado power optimization. Power dissipation can be categorized as static or dynamic. In the simplest terms, you can think of an FPGA as a network of billions of transistors modeled as tiny capacitors. These capacitors consume static power due to small amounts of leakage current when powered on, and they consume dynamic power when they are charged and discharged during normal operation. Besides the device utilization, static power is mainly determined by semiconductor process parameters and the voltage of the power supply. Dynamic power consumption can be modeled as a product of switching activity, clock frequency, overall capacitance, and the square of the voltage supply. Typically, users have fixed timing goals that they need to meet and specified functionality that they need to have in the FPGA. The supply voltage is also fixed in most cases, so the only factor that you have direct control over is the switching activity of the design. But often, it requires deep knowledge of the design's behavior to manually add gating logic that will turn off unused portions of the design. With most complex designs today using unfamiliar IP blocks, this is almost an impossible task. That's why Vivado's power optimization is the perfect choice for minimizing switching activity and thus reducing overall power consumption, with no detailed knowledge of the design required. Vivado performs automatic intelligent clock gating over the entire design, finding sequential elements that do not contribute to the logic results for a given clock cycle. Clock enables and port enables with appropriate gating logic are then used to prevent unnecessary switching on these registers and block RAMs. The original functionality remains unchanged, and timing is unaffected for the most part. Power optimization in Vivado can be invoked either pre-placement or post-placement. The pre-placement option provides the maximum power savings. However, since placement has not occurred yet, it is possible in rare cases that the timing could be affected. The post-place power optimization, on the other hand, ensures timing preservation while saving power. Note that power optimization cannot be enabled in both places. Further, Vivado provides users the options to optimize the entire design or just portions of it. This control is especially useful when there is a need to protect a portion of the design from changes or to preserve timing on a critical module in the design. Users can set up their XDC constraint file to identify these modules for performing the targeted power optimization. Some of the controls offered to the users are the ability to include or exclude instances in the design, identify clock domains where power optimization should focus on, or even control the type of cells like block RAMs or registers that need to be optimized. Now let's jump into the demonstration. We have set a simple Vivado project to illustrate the use and effectiveness of power optimization in Vivado. This is a single port block RAM whose port A is written and read. The design has been synthesized. Let's open the schematic to review the design. Notice that port A enable is tied high, meaning that the RAM is enabled at every cycle, possibly wasting power. Now, let's enable the power optimization option available in the implementation settings of the Vivado GUI. Click on Implementation Settings in the Flow Navigator to bring up the project settings. Notice that there is Power Op Design entry below Op Design. This is the pre-placement Power Op Design. This option maximizes the power savings for the design. If you scroll further down, there is the post-place Power Op Design that saves as much power as possible while preserving timing. For this demonstration, we will select the pre-placement power optimization by checking the is_enabled checkbox. Click OK to exit the dialog. There can be situations where you do not want to optimize power for the entire design. For example, some critical path delays may degrade after power optimization, so you may want to optimize the entire design except for those few paths. Vivado provides an XDC command set_power_opt allowing you to limit the scope of the power optimization. For instance, you can specify that the optimizations should only optimize a particular hierarchy in the design, or you can instruct the tool to optimize only a specific clock domain, or even just a specific cell type like BRAMs. Now let's run implementation. Now that implementation is complete, let's open the schematic and review the BRAM connectivity. Power optimization automatically determined that this RAM is only read under certain conditions and gated the enable with an OR gate. The RAM is only enabled when one of these two inputs is active, thereby reducing the dynamic power. When checking the RAM cell properties, take note that there is now an is_clock_gated property set to true, indicating that the power optimization has optimized this cell. To understand the impact on power optimization of your design, use the report_power_opt command on the Tickle console. This report gives you a quick summary of all instances optimized for power, as well as a comprehensive list of those instances. It also provides a column which indicates whether the instance was optimized by the tool or by the user. To gauge the effectiveness of power optimization, you can run power estimation before and after. To run power estimation, use the report_power command or the interactive report power UI from the Flow Navigator. Notice there are many settings and options, including specifying switching activity and running either vectorless, which is the default, or with actual simulation vectors for greater accuracy. For more information, please review the Power Estimation Vivado Quick Take. Oftentimes, invoking power optimization very late in the design cycle could involve additional time and effort to meet design constraints. To get the most out of your power optimization with the least amount of effort, always enable power opt from the beginning of the design process. This will ensure that you get the maximum benefit from start, as well as minimize the iteration time involved in closing timing. Always constrain the designs as accurately as possible. This will ensure that you're able to achieve the most accurate power estimation, as well as help the tool make wise choices during optimization. As with the most accurate design automation tools, following good coding styles could make the difference between meeting your design requirement and missing them. For instance, try to minimize the use of asynchronous set/reset signal going to the flip-flops and block RAMs. This affects the effective gating of your design for power. Also, use case statements when possible instead of if, then, else, or serial conditional assigns. This will help the tool better optimize for power. Finally, leverage the various power options Vivado offers. Use the pre-place power optimization to save maximum power, post-place to better preserve timing, and the set_power opt command in the XDC constraint editor to perform a more targeted power optimization. So to summarize, Vivado power optimization delivers power reduction using intelligent clock gating with little interaction required. You can automatically optimize the entire design or use more fine-grained controls to pinpoint certain logic for power reduction. This concludes the quick take on Vivado power optimization. For more information, please refer to application notes posted to xilinx.com/power, as well as the related power analysis quick take video. Thank you for your time.